Okay, let's review where we are now. So recall, first of all, the fundamental theorem of line integrals. Says that the integral over c of the gradient of a function f dot dr equals f of b minus f of a, whenever c is a curve going from the starting point A to the end point B. And we use this fact to prove that a vector field f is conservative i.e. f is the gradient of little f for some f, if and only if the integral over c of f dot dr equals 0 for all closed curves C, where curve C is closed if its initial and starting endpoints A and B are equal. Okay, so it follows immediately from the fundamental theorem of line integrals that if f is the gradient of something, then the integral around a closed curve is 0, and going the other way, we had to, given a vector field with this property, we had to define a potential by integrating along closed curve, right, not closed curves, and then checking that it has the correct partial derivatives. So this is a criterion for when a vector field is conservative, but it's not very useful for testing whether a vector field is conservative because there's no way to integrate over all possible closed curves. So it would be nice to have a more practical way of deciding whether a vector field is conservative. So here's an observation. So let f equals pq be a vector field. I should have said this. Let's assume that the components are differentiable functions. So I have a differentiable vector field on a domain D in R2. And the observation is that if f is conservative, then dp dy equals dq dx. And why is that? Well, the reason, so if capital F is the gradient of lowercase f, then what that means is that p equals fx and q equals fy. And then what is dp dy? Well, that's fxy. Because what this equation is saying is that, so the left-hand side here is fxy. And what's the right-hand side? Well, dq dx is fyx. And we know that these are equal by Clairaut's theorem. So if f is the gradient of something, then if the gradient of a function lowercase f, then looking at the mixed second partials of f and knowing that they're equal, that gives you this equation, dp dy equals dq dx. So that's a useful test for when a vector field is conservative. So let's do an example. So is the vector field f equals x squared cosine y x plus y cubed conservative? So the components, this is what we're calling P, and this is what we're calling Q. Okay? If it is conservative, then we must have dp dy equals dq dx. So let's check and see if that's true. So dp dy is equal to minus x squared sine y. On the other hand, dq dx equals 1. And these are not equal. So since these are not equal, we conclude that this vector field cannot be conservative. Because if f were conservative, then by Clairaut's theorem these would have to be equal, but they're not. Okay? So this is a way to prove that a vector field is not conservative. Now you could ask the converse question. So the question, so if f equals pq, and if we do have partial p partial y equals partial q partial x, then must f be conservative? So if this test is okay and does not say that f isn't conservative, do we know that f actually is conservative? Or could it be that f is not conservative for some other reason? So the answer, well, sometimes. So to clarify that, I need a definition. So definition. So I'm not going to say this completely precisely. I'm just going to say the intuitive idea in words. That'll be good enough for this class. So a domain D in R2 is called simply connected if it contains no holes. So for example, if I take a disk, then this is simply connected. If I take a disk and cut out a smaller disk, this is not simply connected. In fact, even if you take a disk and even if you just remove a single point, like if you take a disk minus the origin, then that's already not simply connected. Okay? And then the theorem is that if D is simply connected, and if F equals PQ is a vector field on T, such that dP dy equals dq dx, then F is conservative. So if you have dP dy equals dq dx, then you can conclude that F is conservative as long as your domain is simply connected. We'll see an example later that if the domain is not simply connected, then F might not be conservative. Okay, and we will prove this theorem, but we first need to introduce another theorem which we'll use to prove it, which is called Green's theorem. So that's coming next.